Good morning, Year 10s. Today we are meeting trigonometric graphs, the sine and cosine graph and tangent. We're going to have a little bit of fun with these. It's going to reinforce your understanding of your best friend in maths, the unit circle, which is going to be great. For those who were wanting a video, yes, I confess I forgot to record my Zoom lesson when I talked a little bit through the unit circle. We do have another lesson coming up on it next week. But Mr. Jamison remembered to record his class. So if you didn't see that announcement in Teams, which you should all be checking, you can still find that there's an exercise there with a video from Mr. Jamison to enable us to go through the unit circle. You'll see it on the right there underneath the first unit circle. If you click on that link, it's going to take you right there. But today, we're going to build on our understanding of the unit circle and have a look at how we can use that to actually sketch what a trigonometric function looks like. We talked a little bit about how trig functions are amazing because they repeat the pattern as we go around the circle. They're called periodic functions because they have a period and then they repeat the same thing. So we can use these. You would have seen these graphs on the news or in the newspapers when you're looking at tide heights, when you're looking at sunrise, sunset, temperatures during the day, that sort of thing. These graphs are very powerful for for modeling anything that happens in a periodic way, so in a regular cycle. We're going to start by looking at the sine graph. You can actually go and explore these yourself. There's a link there. But what we're going to do is we're just going to look at this and see if we can get a feel for what the sine graph should look like. What do we need to remember about our trig functions? We need to remember that as this point is going around the circumference of our circle, the x-coordinate is the cosine of the angle made with the positive x-axis, and the sine is the y-coordinate. And we get that because this was the hypotenuse. Remember, cosine is adjacent. So this is the adjacent side here, and the adjacent side divided by the hypotenuse gives me the cosine. Well, if the adjacent side is 1, if the hypotenuse is 1, then the adjacent side divided by 1 is just the adjacent side, and that's why cosine is equal to the x-coordinate as we go around that circle. If we want to think about the y-coordinate, well, sine is found by doing the opposite divided by the hypotenuse, but when the opposite side is 1, when the hypotenuse is 1, the opposite side divided by 1 is just the sine of theta. So as that point whizzes around the circle, the x-coordinate's giving me the cosine value, the y-coordinate's giving me the sine value, and that's why we are able to actually calculate values for angles greater than 90 degrees. So we have another angle off in the second quadrant over here, and we measure the angle from the nearest. Actually, what I'll do, I'll make it the same angle, the same size as the other angle. We'll make it theta degrees away from our closest x-axis again. And what do we notice about the x and y coordinates here? Well, looking at the y coordinates of each of those points, they are at the same height. So the y coordinate of this point is going to be equal to sine theta, but the angle that I was actually working with was 180 minus theta. If I go round to 180 degrees, a straight angle, and come back theta, that's how I could get to that point. So the sine of 180 minus theta is exactly the same as the sine of theta. The cosine of 180 minus theta, the x-coordinate here, well, these are similar triangles. Got a right angle there. In fact, they're congruent triangles because I've got a right angle, the hypotenuse, and one other side. We've already established that's the same. What we can find here is the cosine is the same length. The length along the x-axis, that length to the left, is the same length as the one on the right, but it's in the negative direction. So from that we could conclude sine of 180 minus theta is exactly the same as the sine of theta. But the cosine of 180 minus theta is negative cosine theta, because it's the same size but in the negative direction. And again, if we plot that point into quadrant 3 and quadrant 4 using the same angle, again theta degrees away from the closest x-axis, so that point, it's now going to be 180 plus theta, so my coordinates will be cosine of 180 plus theta, and the sine of 180 plus theta. Well, we can see the x-coordinate is the same size again, but in the negative direction, so we can write cosine of 180 plus theta is the same as negative cosine theta. What about the sine, the y value for 180 plus theta? Well, that height there, and this height there, they're all the same size. We've got congruent triangles, so they're all the same size. But this time my y-coordinate, if I read across to the y-axis, it would be negative, wouldn't it? You can see it's going to cross the y-axis at a negative spot. So the sine of 180 plus theta is negative sine theta. So this was quadrant 2. This is going to be quadrant 3. And down here we'll have a look at what about angles in quadrant 4. Got to make sure my 3 doesn't look like a 4. Got a bit grubby there. Alright, so same size angle again, theta degrees away from the closest x-axis. So let's call this one the cosine of 360 degrees minus theta. That would be my x-coordinate, and the sine of 360 minus theta would be the y-coordinate of that point there. Well, the cosine, the x-coordinate, it's back to being positive again. And in fact, it's exactly the same as what we had in the first quadrant. So the cosine of 360 minus theta is the same as cosine of theta. The sine, the y-coordinate, well, it's the same size, but it's in the negative direction, so it's equal to negative sine theta. So that's what the basics of our unit circle helps us with. I like to just think about it in terms of x and y coordinates. So I know in quadrant 1 the x coordinate cosine is positive and sine is positive. In the second quadrant over here, I know my x coordinates are negative because I'm to the left. And I know my y coordinates are positive because I'm still above. In the third quadrant, I know that both the x and y coordinates are negative. And in the fourth quadrant, I know my x coordinates, I'm to the right of the y-axis, so the x coordinates are positive, but I'm below the x-axis, so the y coordinates are still negative. So I just remember them that way, but a lot of people like to use a little mnemonic to help them. And one they can use is all students take crack. Obviously not true at all. All stations to central is another one you might want to use there. But that's just a way. This is telling us that all of them are positive. Oh, my pen is struggling today. At least you heard me say positive, right? The only sine is positive in quadrant 2. In quadrant 3, it's tangent that's positive, and in quadrant 4, it's cosine. Now, if you want to think about why tangent's positive, remember it's where it touches the tangent axis way over on the right here. Imagine I drew that perfectly. In quadrants 1 and 3, if I continue the radius through the origin, it's going to hit the tangent axis in a positive area. When I go in quadrants 2 or 4 and I continue that radius down, it's going to give me a negative value. All right, this is getting messy and complicated, but that all stations to central, all positive, sine positive, tangent positive, cosine positive. That's another good thing to help remind you of what we're doing when we do our trig equations. But I promised you to talk about trig graphs, and I've already gone nearly 10 minutes just recapping the unit circle. So let's lift my game a bit here and see if I can get onto those graphs.